we have Brodie Pearson. Brodie got his PhD in 2015 from the University of Reading, and then spent a few years as a postdoc at Brown University. And since 2019, he's been assistant professor at Oregon State University. Today, he's talking to us about a new method for diagnosing large-scale energy transfers on Earth and other planets. So take it away, Brodie.
Great. Yeah, as Jonathan said, I'm going to be talking about this new method that we've developed for looking at how energy is transferred between scales on, in general, geophysical systems. But before I start, I'd like to thank Jonathan for inviting me. These seminars have been really interesting so far. And actually, I'm going to, if any of you were at Drew's talk 2 weeks ago or the talk 4 weeks ago on Jupiter, I'm going to try and make some connections to those talks throughout this one. So you might recognize a figure or two or some concepts that I discussed, and I hope that that is useful for you. But I'm not going to assume that you saw those talks, and I'm going to try and cover everything from the bottom up. So this, I'm quite excited to be presenting this topic today. So with the pandemic, I haven't really had a chance to present any of the results I'm going to talk about today in a full format talk, and so it's exciting, but I also encourage you to ask any clarification questions in the chat, because this is my first time going through this topic fully in a talk. So I realized I might have blind spots. So please feel free to write those in, and I'll try and spot them as I go through. So I'm primarily an oceanographer, and so I'm going to motivate this new method from the perspective of large-scale ocean turbulence. I'm going to talk a little bit first about what energy transfers are, particularly turbulent inertial cascades, and why they're important, some of the challenges of measuring these cascades in the ocean, and the existing techniques for measuring them and some of their limitations. And then I'll use that as a lead-in for the new method that we've developed to diagnose transfers of properties between scales, which I'll test with some idealized simulations, and talk, if I have time at the end, about some of the applications that this method could have and is having for us when we're applying them to more realistic geophysical systems on Earth and on Jupiter. So start with, I'm presenting a new method for diagnosing energy transfers, but what are energy transfers in planetary systems and why do they matter? So if we think about how energy is supplied to planets, it's generally supplied by solar heating at the planetary scale. So the sun heats the equator more than it heats the poles. That differential heating causes a difference in temperature between the equator and poles. When you have fluid on a planet, that temperature difference creates a density difference, and that lateral change in density between the equator and pole is a large source of potential energy. So effectively, the solar heating is providing potential energy at a planetary scale. And then that potential energy is extracted by various mechanisms or converted by various mechanisms into kinetic energy. And that kinetic energy fuels many different types of turbulence at a wide range of scales. And eventually, a lot of that energy, that kinetic energy, ends up at the smaller scales where it's dissipated by molecular viscosity. So there's kind of a complex cycle of transitions between potential energy and kinetic energy at a range of scales that eventually lead to a lot of that energy being dissipated at molecular scales. And the pathway that energy takes is actually quite important for the climate system. So the extraction of potential energy to fuel turbulence affects the mean structure of the oceans and atmospheric systems by adjusting those lateral gradients in density that I was mentioning before, and extracting the potential energy from those gradients. But understanding how and why the energy transfers occur differently in different places and what their magnitudes and directions are in different places is also important for understanding the mechanisms of these transfers, which helps us to understand how, if the Earth system changes in the future, what kind of new equilibrium might we get? So So these turbulence energy extractions can actually compensate for some of the changes in the Earth system or amplify them if they're positive feedback mechanisms. So really what I'm going to be talking about today is a new method to figure out how turbulence is transferring energy between scales. And I'm really going to be focusing on one specific type of turbulence. It's called mesoscale turbulence, and it's the largest scale of ocean turbulence. It has a lot of similarities to other large-scale geophysical fluid dynamics, which are in geostrophic balance, where pressure gradient forces balance Coriolis forces. And this mesoscale turbulence in the ocean really manifests as largely as turbulent eddies. These eddies can be anything from tens to hundreds of kilometers in size, and they can persist for days to months. And this video that I'm showing here is actually satellite observations of the kinetic energy contained within those mesoscale motions. It's a year-long data record. It's stepping through right now, and you can see that there's a lot of features occurring at small scales. So there's little patches of energy popping up in places where mesoscale eddies are being formed or dissipated, and there are features that are being affected around by the flow. And so there's a rich variety of dynamics at the mesoscale. And there's actually a much richer variety than shown in this figure, because these satellites are actually missing about an order of magnitude of smaller mesoscale motions in the ocean. And so if we were able to observe the ocean at a finer resolution for this long period of time, we would actually see even more variety and richness in the dynamics happening here. But these dynamics are turbulent, they're kind of chaotic, there's fluctuations that are hard to predict. And these mesoscale eddies are being energized by the potential energy gradient, the large scale potential energy that I mentioned before. And they're energized at a particular scale. That scale is called the deformation radius, which I call L here. And that deformation radius depends on the stratification of the flow. It depends on the depth of the flow, and it depends on the Coriolis parameter. So there's a latitudinal dependence. This deformation radius is very large at the equator and small at the poles. And the dependence on stratification and depth means that it also varies regionally quite significantly. So we have this mesoscale ocean turbulence that plays a role in moving energy between scales, which I'll talk about in a second, and it's being energized at a specific scale. So once that energy gets supplied at a scale, how does it get moved by mesoscale turbulence to other scales? We can think of this kind of conceptually as what if we start with one turbulent eddy at that deformation radius that's been energized by the background potential energy. It's got some conserved properties like energy and enstrophy. So energy is the square of momentum. Kinetic energy is the square of momentum. It's conserved property. Enstrophy is a similar quantity that depends on the rotation rate of fluids. So when we're thinking about eddies, we're thinking about fluid parcels that are rotating. And that rotation rate is a measure of angular momentum that we call the vorticity. And the vorticity squared creates this conserved quantity entropy. Now, this turbulent eddy is being fed energy and entropy at the deformation radius, but it's sitting in a turbulent flow, and that turbulent flow can advect and deform the eddies. It can cause them to shrink or break up into smaller eddies, and that transfers its properties, its conserved properties, to those smaller eddies, effectively causing a transfer from one scale of motion to a smaller scale of motion. You can imagine that process continuing and those eddies being broken down or shrinking further. And this is where we get the idea of a turbulent cascade from one scale to another. So the advection by chaotic or highly nonlinear turbulent motion causes these features or turbulent features to shrink or expand in size and transfer their properties to a different scale. So when we're thinking about mesoscale turbulence, the main cascade that we think of as transferring properties to smaller scales is what we call a downscale cascade of entropy. And so these systems are physically constrained as to what they can transfer and in what direction. But for the mesoscale, it's really this transfer of entropy to smaller scales that happens. But you could also imagine something happening in the other direction, where we start off with that eddy at the deformation radius, and the flow causes it to coalesce with other eddies or expand in size. And that creates an inverse cascade to larger scales. And in the mesoscale turbulence regime, we often think that this inverse cascade is predominantly a transfer of energy, kinetic energy, from small scales to large scales. And so conceptually, those are really the two types of cascade that we expect to see in mesoscale turbulence. What I'm going to talk about today is ways of measuring the magnitude and scales at which those cascade occur. So how quickly are things being transferred between scales? And this kind of a conceptual overview of cascades. We can actually look at them a little bit more mathematically. So these cascades are driven by advective processes transferring properties between different scales of motion. When we normally think of advection, we think of it in real space. We think of advection as moving something from one place to another. When we're trying to think about cascades, it's more natural to think in Fourier space. So those of you who were at Drew's talk 2 weeks ago will recognize this figure, which is showing this concept of Fourier decomposition, where we can have a spatial data set, some variable that depends on position, and we can break it down into a discrete number of waves with different frequencies and amplitudes, or different wave numbers, wavelengths and amplitudes. And that's Fourier decomposition. So in this case, you can separate that red signal on the left into three, as being the sum of three different waves with different wavelengths and amplitudes, shown on the right. And so when we're thinking about advection in this Fourier space, what we're thinking about is the advection transferring properties from wavelengths of a certain, or waves of a certain wavelength, to waves that have different wavelengths. So there's kind of a change in amplitude of one wavelength and a corresponding and opposite direction change in amplitude of another wave. And so that's kind of transferring properties from one scale or wavelength to a different scale. When we do that, we can form equations for the energy of the flow in Fourier space, and we end up with this quantity pi here, which is the spectral energy flux. And that's a direct way of measuring this rate at which turbulence is transferring energy between scales. And we can write that mathematically as a function of the Fourier transforms of, in this case, velocity, and of the advection operator. So that u dot grad u. That advection operator is something we're going to come back to a little bit later. Now, it's great that we can calculate these spectral energy fluxes directly. Unfortunately, a lot of the data that we have, or essentially all the data that we have, is not very amenable to this kind of calculation. And so we need different routes to estimate how properties like energy are being moved between scales. And that's a lot of what the rest of this talk will go over is the existing methods that we have to estimate this cascade rate, and the new method that we're going to present today. So we have this, we want to figure out how quickly properties are being moved between scales by turbulence. I am primarily a numerical modeler. And so my first answer to that question is, what can models tell us? Yeah, I see a question, a hand raised.
Yes. Brodie, can I quickly ask you, so you talk about energy, but from the last formula I can see you talk about kinetic energy. What about potential part? Will you say any words on the potential energy transfers?
Yeah, that's a great question. So everything that I talk about today is going to be focused on kinetic. So I'm going to be talking about 2D dynamics where there is no potential energy. We're just looking at the kinetic component. But there is work that we're doing at the moment to identify whether we can disentangle those potential and kinetic energy transfers. I'm not going to talk about that today, but it is an important part of expanding the methods that I'm going to present to more general geophysical systems.
Yeah. Okay, thank you.
Thank you for the question. So yeah, when I refer to energy from here on out, I'm actually referring to kinetic energy, although I did mention potential energy back at the beginning of the talk. Right, and so we have this way of calculating the spectral transfer of kinetic energy between scales, but we can't normally calculate that for most of the data sets we have. As a numerical modeler, my first question is to ask, what can models tell us about these systems? They can tell us some things, but not everything. And so we can actually run global ocean models at a scale that resolves that deformation radius in a large fraction of the ocean. And so we can create mesoscale eddy-rich turbulent fields within these models. And this is an example of one of those simulations. What I've plotted here is a measure of grid scale dissipation, which is actually representing the rate at which properties, enstrophy in this case, is being cascaded to smaller scales. So in places where the field is red, there's a rapid transfer of enstrophy to smaller scales. And in places where the field is blue, there's a much lower rate of transfer of entropy to smaller scales. And the main result from this figure is that there is a huge amount of spatial variability in how quickly properties are being cascaded from one scale to another by ocean turbulence in these numerical simulations. Now, this kind of hints at the regional variability of these properties as being an important thing to measure, which I'll come back to in a few slides' time. But these models aren't actually telling us the whole story because there's a lot of dynamics that they're missing. So they might be resolving mesoscale turbulence, but it's not clear that they're resolving the same turbulence that the real ocean experiences. And to give you a kind of overview of why that is, I'm going to show you a plot which I made of the resolution of global ocean models, the horizontal resolution, as a function of time. And so what I've got here at the moment is resolution on the y-axis, so the rough width, the approximate width of horizontal grid cells of these models, and the year on the bottom x-axis. And this is a figure that I made in collaboration with Baylor, who is watching this talk at the moment. And so what I've plotted at the moment is a range of scales, that orange region, which roughly encapsulate the range of deformation radius, that energy supply scale for ocean turbulence, for mesoscale ocean turbulence. And so at that scale, the mesoscale eddies get supplied with energy and entropy, and then it gets moved to different scales, which is what's denoted by those arrows there. But really, to resolve mesoscales, you actually need, to resolve them globally, you actually need several grid cells, finer resolution than that deformation radius, because you need to be able to resolve the eddies themselves that are getting produced by instabilities at that scale. So what I've put here is some lines denoting where you might consider the mesoscale energy supply to be well resolved globally in those global ocean models, as well as some other processes. So sub-mesoscales are the next smaller dynamical regime from mesoscale turbulence. And they interact with mesoscale turbulence, transferring energy backwards and forwards between mesoscales and sub-mesoscales, and then boundary layer turbulence, which is the classical kind of three-dimensional turbulence, or is closer to the classical three-dimensional turbulence that's often that most turbulence concepts are framed around. So yeah, we have these scales of what we need to resolve what resolution we need in order to resolve different processes. Now we can plot the resolutions of global ocean models on this plot too. So the black dots that I've plotted here are cutting edge climate models. They're the ones used for different panels of different reports from the IPCC, the Intergovernmental Panel on Climate Change. And so that group, the IPCC, produces a different report every 5 to 10 years. And with each of those reports, they run a suite of simulations of global ocean models to simulate and project climate change going into the future, as well as historical climate change. And so each of those reports is released at a specific time, which is why there are several columns of those black data points up there. And each data point represents the resolution of a specific ocean model from a specific ocean modeling center that goes towards that IPCC report. And as you can see, as time's gone on, a lot of those models have began to transition into increase their resolution and transition into the mesoscale energy source resolving scales. But none of them are really down at that true global mesoscale resolving regime yet. What I also plotted on here was a blue star indicating an ultra high resolution ocean model simulation that was run in the past few years. It's got about 2 kilometer resolution, which is actually right where we expect it to be resolving the mesoscale globally. The downside to that model is that it's really computationally expensive. So we have, it basically is run for about 1 year and is not coupled to an ocean, it's just an ocean model that is not coupled to an atmosphere like the climate system models that are represented by black dots. And actually, if we wanted to run that simulation for the range of experiments and timescales that the black dot simulations are run for climate analysis, then we would actually require about 1,000 times, at least 1,000 times more computational resources to run that. And we can look to the future and of how's resolution going to change. These are a couple of different fits. One of them's Moore's law and one of them's a fit to the finest resolution. So they're both very optimistic projections of how our highest resolution climate models might evolve their resolution going forward in time. And it's not going to be for several decades before these models can fully resolve mesoscales globally. And it's probably not going to be until close to the end of the century that we can resolve sub-mesoscale processes. So that's important because those sub-mesoscale processes might actually interact with the mesoscale energy processes and cause changes. They might have a large impact on the energy cycle of the mesoscale. And so we should probably be resolving them before we fully trust our model's energy cycling at the mesoscale. So global models won't be able to fully resolve mesoscales and mesoscale energetics for a long time. So the question that I'm going to ask for the rest of this talk is, can observations be used to measure transfers of energy and entropy between scales? So to ask that question, we really need to look at what kind of data we have from ocean observations. And really, the ocean is hard to observe. We're thinking about measurements in the interior of the ocean. You either have a fixed location that you're measuring consistently, like a mooring, as shown in the top left panel here. There's several moorings off the coast of Oregon that are run by Oregon State University and the Ocean Observatories Initiative. Or you have some instrument that kind of measures properties locally and moves through the ocean. So that might be a ship. It might be a glider, like the one moving between the moorings in the top left panel, or it might be an Argo float. There are several thousand of those Argo floats across the global ocean. Problem is those methods just give you information about maybe a line of data points rather than a full field of data points. Now it's a little bit easier to measure the surface of the ocean. Drew gave a really nice talk a couple of weeks ago about drifter observations of the surface of the ocean, but that observation campaign was confined to the Gulf of Mexico. It was very region specific. It's hard to look at mesoscale processes using in situ observations at a global scale. But you can also observe the ocean surface dynamics remotely. So we use satellites for that. Our current satellites can resolve things that are maybe 100 kilometers and larger, but future satellites are expected to be able to measure much smaller scales. So there's a satellite going up this year that can measure ocean dynamics down to about 15 kilometers. The downside to those satellites is that they tend to repeatedly travel over regions of the ocean in a specific direction, like this figure in the bottom left is showing. So they often do transects. They measure information, but only in a line of points below the satellite. But those new satellites that they're sending up provide us with a really neat opportunity to potentially resolve a lot more of the mesoscale energy supply scales. So I've plotted that here. The blue line is that resolution of the new satellite that's planned to go up this year. So we're going to be able to potentially resolve a lot more of the energetics of mesoscale turbulence. The problem is we may not have the tools at the moment to actually interpret those observations accurately as with respect to kind of quantifying the energy transfers from those observations. And so I'm going to be talking today about a particular method to do that. Now, the methods that we do have to figure out cascades at the moment are often tied to gridded data. So you really need a gridded set of data to analyze. So I mentioned Fourier analysis. We can calculate the spectral flux directly. Typically, that requires some regularized or gridded data, and it assumes statistical homogeneity of the flow. The properties are the same everywhere. There have been some other cool advances recently, like coarse graining, where you have some gridded data set about the flow field. You filter it at some scale using ideas from large eddy simulation methods. So you filter out the smallest scales of that gridded data set, and then you look at how properties are being transferred between those filtered scales and the subfilter scale. So that requires gridded data and can only really be used on isotropic flows at the moment. So the question that I'm going to ask is, what can we do if data is irregular, like all of the ocean observations that I talked about before, or if the flow is anisotropic? So anisotropic basically means that properties vary depending on what direction, or the flow looks different depending on what direction you look in. And all geophysical flows are anisotropic to at least some degree. And that's because they're all lying on a rotating planet. That planet is rotating around a specific axis. And so as, let's say, a mesoscale eddy moves from the equator to the pole, the projection of its own axis of rotation becomes more or less aligned with that planetary rotation, causing dynamical effects. I see another question. Yeah.
Yes, can you comment a bit more on the coarse graining? So if Rossby deformation radius changes from few kilometers near in Arctic to a couple 100 kilometers on equator, should we coarse grain according to RD somehow? Do you see my point?
Sorry, could you repeat that once more?
So when we coarse grain the data, do we have, to your opinion, connect this coarse graining to the Rossby deformation radius, which changes by 2 orders of magnitude from equator to pole?
That's a good question. So the coarse graining method has so far been used to look at specific local regions, and those were chosen. Well, when you're looking at a specific local region, you can estimate what the Rossby deformation radius is and deal with that. But yes, yeah, if you were trying to do this at a global scale, you would have to think about that. Yeah.
Thanks.
Yeah, and so all geophysical flows are anisotropic to some degree. And the method that I'm going to show today is one of the first that can estimate these transfer rates in anisotropic flows. So this method is based on structure function analysis. And to give you an idea of what structure function analysis is and where it is right now, I'm going to give you a quick overview of what a structure function is. And so if we want to diagnose cascade rates from the irregularly spaced observations that we have, it's probably better to approach that from a perspective of spatial evaluation rather than Fourier space evaluation. So working in real space is a little bit easier than working in Fourier space. So we might have an observation at some point, and then at position X here, and an observation at another point, which is separated by some distance R. And we can calculate the differences in properties between those points. So I represent that here by a delta. And if you're thinking about temperature and salinity, that's an easy thing to calculate a difference of. If you're thinking about a vector like velocity, then you need to choose a component of that velocity to take a difference of. And it turns out that the most useful one is to look at the velocity in the direction oriented along that separation vector. And when you do that, you can calculate these delta terms. You can multiply them together to find kind of correlations, spatial correlations in these differences. And when you do that and average those products of delta terms, you end up with structure functions. And structure functions are neat because there's actually some turbulence theory dating back as far as the 1940s, connecting these structure functions to transfer rates of energy and entropy. So in 3D turbulence, there's this law that Kolmogorov figured out, which was that the downscale transfer rate of kinetic energy is related to the third order longitudinal velocity structure function. But we're talking about larger scale, more two-dimensional flows at the moment. And so there are actually a couple of laws that can relate transfer rates to structure functions in these flows, one for the kinetic energy transfer to large scales and one for the entropy transfer to smaller scales. So these are relations that I'm going to call the classic structure function analysis relations. And they have a couple of drawbacks. The one that I'm going to focus on today is that they're derived by assuming that the flow is isotropic. And as I mentioned, geophysical flows are inherently anisotropic to varying degrees. And so I'm going to use that as my bouncing off point for presenting this new method that we developed, a new type of structure function for detecting transfer rates. And I'm going to test that structure function in some simulations of anisotropic two-dimensional flows, and then talk about some extensions that we're working on with these structure functions. So these structure functions are what we're terming advective structure functions. They basically depend on correlations between velocity differences, these deltas of U, and delta A, where A is an advection operator. So that advection operator is written down to the right here. And these structure functions tell us something about in this case, the energy transfer rate to large scales. That's what this epsilon mu represents. So these structure functions have one kind of large caveat, which is that in order to calculate them, you need to be able to estimate the gradient of properties locally. So you need to be able to estimate this advection operator at both the locations you're taking differences between. It turns out that a lot of observational methods could actually estimate that local gradient, which is not something I'm going to talk about today. But it is a caveat if you're working with certain types of data set to estimate that. But like I'm going to show, if you can estimate this new type of structure function, then it comes with a whole host of benefits over classic methods. And Stephen, I see your question, but I'm going to wait till the end to take that one. And one of the big bonuses of this new structure function is that when deriving it, you don't have to assume isotropy. And as I'm going to show, that actually means that it works really well in anisotropic flows, unlike classic methods. And this is all work from a paper that I wrote last year with Jenna Pearson from Princeton and Baylor Fox-Kemper from Brown. And there's also a bonus relation that comes with this that tells us about how enstrophy can get moved to smaller scales. And so in this case, this eta mu term is the rate of entropy transfer to small scales. And I'm going to be testing both these functions in the next couple of slides. So I mentioned that we're going to test these new structure functions and whether they can actually predict the cascade rates using some numerical simulations. I'm going to use software that's coded in Julia that I wrote in collaboration with some other people like Navid Constantinou and Greg Wagner. And this is an open source piece of software that can simulate a bunch of different idealized geophysical dynamical systems. So I'm going to be talking about two-dimensional simulations today, but it can also simulate a variety of quasi-geostrophic systems, which is something else we're using to evaluate these structure functions. These systems are in a periodic domain and are solved with spectral dynamics. And they can actually, one of the nice things about using Julia is we can run these on CPUs or GPUs very easily. Now, I'm going to say that one of the benefits of using numerical models, first of all, to evaluate these structure functions is that we have the full field of data. We know what the velocity and vorticity fields are. In this case, this plot here is showing the vorticity field of one of these simulations. And so from that, we can calculate the spectral fluxes exactly and compare the structure function estimates of those fluxes to the fluxes themselves. And so this is an example of the spectral flux of energy from one of these simulations. So I've also written the governing equation of this system at the bottom here. The governing equation controls vorticity evolution, which is vorticity is represented by omega here. And we have advection of vorticity. We have this beta term, which I'll mention or explain shortly. And then on the right-hand side of this equation, we have forcing and dissipative terms. And so we force the system at a specific scale. That supplies energy and entropy. Then some of that energy goes to smaller scales. And that's a result of that downscale enstrophy cascade. And entropy is the rotation of fluid. It obviously requires a little bit of energy to go with it to supply that rotation. So a little bit of energy goes to small scales and is dissipated by a viscous term represented by the nu in this equation. And then a more significant fraction of the energy supplied to the system is cascaded to larger scales through the inverse energy cascade. And that's the rate of that cascade is denoted by the red dashed line here, and we denote it with epsilon mu. And to dissipate at large scales, we use a hypoviscosity represented down here in the equation by the mu term. And a lot of that dissipation happens at a scale which I denoted with this other blue dashed line on the left here. So we have a system that's forced and dissipative and has well-developed inertial cascades. We also run this simulation for several large eddy timescales and have a whole bunch of snapshots so we can get an idea of how uncertain these measurements are. And that's represented by the, or how much temporal variability is, that's represented by the gray shading here. So that's the energy dynamics. We have a well-developed inverse energy cascade where the spectral flux of energy to larger scales is pretty consistent across a wide range of wave numbers. We also have a bit of a downscale entropy cascade here at some rate, eta. And this is the entropy spectral flux plotted here. And so most of that entropy is going from the forcing scale to smaller scales. And I mentioned that we have this equation of motion at the bottom and there's a beta term in there. So that beta term or beta term is the switch that we use to introduce anisotropy to the system. So it represents the planetary vorticity gradient that results from the fact that as you move from equator to pole, you become more aligned with the axis of planetary rotation. And we run a bunch of simulations. I'm going to really focus on one of them here, but we run simulations ranging from weakly anisotropic, like the figure on the right, to strongly anisotropic, where we develop jet-like structures in the vorticity field, similar to those that you might see on, or they look similar to the jets you might see on Jupiter or Saturn. And we take a bunch of observations in different directions. So we want to know if we were to measure these fields with a satellite in a specific direction, or with ship tracks that are repeated in a specific direction, or gliders, or other observations that might have a specific orientation, would we be able to detect those spectral fluxes that I showed were well developed in this system? Like, how much does your estimate of a spectral flux depend on the direction that you measure a flow in? And so this is an example of the estimates of the spectral flux of energy that you get from classic structure function methods. So there are 4 lines on this figure, or actually, let's start that. There's that red line, which represents the inverse cascade rate of energy, which we got from the spectral flux. That's how quickly energy is being moved to larger scales. And that range that the red line is plotted between is the range of that inverse energy cascade. So I did that because we flipped from wave number to separation distance here. So it makes it a little bit easier to see where that energy cascade range should be applying. So there are 4 lines plotted here showing that estimate as a function of separation distance. And those lines correspond to each of the 4 directions of sampling that I mentioned we were going to try. Basically, what you see here is that classic methods depend significantly, the estimates that you get from classic methods depend significantly on what direction you sample a flow in. But if we look at our new structure function method, these lines all overlay each other, at least at the smallest scales, at scales below those jet scales. And close to the forcing scale, which is really the middle blue dash line, those lines, the new structure function methods do a pretty good job of oscillating around the exact spectral flux value. And so it looks like these advective structure functions can provide some utility in diagnosing energy transfers, even in very anisotropic flow, and they're not as sensitive as to sampling patterns as the classical methods. And another thing is that they have a lot less temporal variability, which is a cool result that comes from the vorticity dynamics and incompressibility that I'm not going to talk about today, but I have a backup slide if anyone is interested in talking about that. The other thing I want to note is, or actually, is those oscillations. So the oscillations actually correspond to something that Drew presented a couple of weeks ago, and their frequency is tied to the forcing scale. And so potentially we could use measured oscillation frequencies or oscillation wave numbers to backtrack at what scale the flow is being forced. So that's kind of a validation that these structure functions can detect the energy transfer rates in anisotropic flows. But now I'm going to also show whether they're useful for enstrophy flux diagnostics. So enstrophy is getting moved to smaller scales in these flows. And to do that, we have a slightly different simulation where we created a more well-developed entropy cascade. So we moved the forcing to larger scales, and we ended up with this situation, this simulation down in the bottom right, where we have entropy. It looks a bit smoother than the simulation before because our forcing is at a larger scale, and so our entropy is now distributed across larger scale motions than the previous simulation. But in this situation, we have an entropy cascade that spans about an order of magnitude of wave numbers. And so we can go and look again at how structure function methods handle, or whether they accurately approximate this cascade rate of entropy to smaller scales. And using classic structure functions, we see a similar thing as before, where the estimate of cascade rate that you get is very sensitive to the direction that you sample in. But with the new structure functions, they seem pretty insensitive to that sampling direction. So the new structure functions are shown on the bottom here. And they get pretty close to that enstrophy cascade rate downscale. And so we think that's a really cool result. We seem to be able to use these structure functions to estimate energy and entropy transfer rates in anisotropic flows in a way that doesn't depend on the sampling pattern that you use to sample that flow. And so that's the main result of our method, that we have this new method that seems to be more amenable to application in realistic flows than existing methods for estimating transfer rates between scales. What I'm going to show now is a little bit of work that was led by an REU student working with me from Johns Hopkins, Natalie Rodriguez, along with a graduate student, Cassidy Wagner from Oregon State University. And what we did was we said, okay, maybe we can test out whether these new structure functions can be applied in a real geophysical system. And so we thought a cool system to try it out in would be the Jovian system. So looking at whether these structure functions can be applied to Jupiter. The reason we chose Jupiter was because we have really nice data from the Cassini mission that measures vorticity, which this is the vorticity field plotted here. You can see the great red spot down in the bottom left, and you can see that banded structure in vorticity, just like the anisotropic simulations I ran. And we also chose this because people have used classic structure function methods to estimate cascade rates in Jupiter's atmospheric flow. So we thought it would be a great test case for the advective structure functions too. And so what I've plotted here on the bottom panels are estimates of the inverse energy cascade rate using classic structure functions on the left and new structure functions on the right. And there's a whole host of lines here. It looks like a bunch of spaghetti. Those lines basically represent sampling of different locations or orientations. And the blue and red lines are the global estimates using global measurements. And the main point to take away from here is that the new structure functions do show a lot less variability, particularly between the forcing scale and the jet scale, which are those two black dashed lines that I plotted here. And Jonathan, I see your estimate. I'm wrapping up momentarily. And we can compare this to other estimates of the inverse cascade rate between those two dashed lines. So actually this paper by Young et al. Estimated it using a spectral approximation, estimated the cascade rate of energy using a spectral approximation, and they ended up with something that sits around 3 or 4 times 10 to the minus 4, which is actually pretty interesting. Our advective structure function results seem to lie between the much noisier classic structure function results and the spectrally estimated results. So we're looking into why that is now. So I'm actually going to skip over that little slide and just go to my summary, which is that hopefully I convince you that it's really challenging to measure the transfers of energy and entropy between scales, particularly in the ocean, due to the complexity of the flow and the sparsity of data. We developed some new advective structure functions that can be used to estimate those transfer rates. And based on numerical simulations, this new method works under strong anisotropy, where classical methods fail, and it doesn't depend on your sampling direction, converges faster with less data, so it's more statistically robust, and it's potentially well suited for some oceanic and planetary observation types. And we are still working on applications to other geophysical flows, like looking at the potential energy, kinetic energy, combined energetics in these systems. So with that, I'm happy to stop and see if anyone has questions.
Great, thanks so much, Brodie. Let's hear some questions.
Do you want me to take Steve Griffith's question first?
Yeah, why don't you do that one first? Chat? Yeah, sure.
Yeah. So Steve said, are you taking into account the sphericity of the planet when taking differences of vectors? When moving to a sphere, it's important to note we cannot simply take the difference of vectors when they live at different points on the sphere. Yeah, that is a great question. So we have looked at that a little bit in terms of the thinking about how we can derive analogous structure function relations on the surface of the sphere due to the changing direction of projections. It's a hard problem because in some ways that change in, if you're talking about the change in orientation of the vorticity axis, then that doesn't really matter so much because the flow is constrained to, although the flow is just moving along that surface and the vorticity axis is always pointing away from the surface. But if you're talking about velocities, then yes, we need to do something smart when thinking about separation distances between 2 points, because it could be that the latitudinal band, a zonal band is not the shortest distance between 2 points, and that's something that we did consider in the Jupiter data, was looking at those separation vectors, the shortest separation vector between 2 points. Although in that case, if you're arcing over the planet, you might have a separation vector that spans multiple jets, or it might cut through one of those other jets, and so it's hard to know how physical that is. I see a question from Ben as well, which is about the new advective structure function requires calculation of derivatives. Are there issues or concerns about handling that derivative from sparsely sampled data? Yeah, I think that is a great question. We've tested in numerical simulations, one of the nice results is that we've tested what happens if we increase the stencil size that we use for that grid. So if it's an order of magnitude larger than the grid scale or at the grid scale of the model, and that doesn't affect the estimates of the inverse energy cascade rate. And so that's neat. We can take derivatives at different, our derivatives don't have to be at a specific scale, but they probably should be derivatives representing the mesoscale flow derivatives rather than smaller scales. In terms of estimating that, there are some data sets that could be hard to estimate local derivatives from. But there are novel ways that we could approach that, like with moorings using Taylor's frozen eddy hypothesis, or there are actually connections between that advective term and the Lagrangian derivative that drifters measure as they move through the ocean. And so, yeah, there are lots of things to explore in that regard. There are probably going to be places or data sets or observation platforms where this really doesn't work, but we're hoping that there will be a significant number where we can utilize that.
I have a question for you, Brodie. The oscillations that you showed in the estimate, in the new estimates, you have this kind of square-like true flux, and then you're seeing these oscillations. I'm not exactly sure all the details, but it just reminds me of what you see in spectral analysis, where you get this these side lobe effects arising from kind of like truncation of a infinite length process into a finite length. Anyway, I'm just curious if you think that those are like some artifacts of the estimation method that are potentially treatable, or if you or something else.
Yeah, I think that there are, my gut feeling is that there are real artifact of the fact that we're looking at something that is inherently exists in Fourier space, but we're looking at it in real space. So Dhruv's talk last week, he discussed how they actually have some really nice structure function developments that are improving. In that case, how we understand so in Dhruv's work, they directly transform the spectral flux into a structure function, and when you do that, you see that there's a part that depends on, in two-dimensional flow, that depends on Bessel functions, which basically introduce an oscillation in the structure function that you calculate. Now, what they've done is only for isotropic flows, and so we're not really sure how to implement an analysis like that or a theory like that in anisotropic flows. But one of the neat results that I didn't really get to talk about much is that these oscillations are tied to the forcing frequency. I said that we changed the forcing frequency in some simulations and saw the scale of these oscillations change. And so you can potentially look at what the frequency of those oscillations are if you're measuring maybe the larger scales and feed that back to infer what scale you're being forced at. So I see it as an opportunity, not just an artifact.
Cool. And you have a question in the chat from Daphne.
Yeah, Daphne, that is a fantastic question. So we were actually inspired by a short theoretical paper that we saw that derived something analogous to this anisotropic structure function for magnetohydrodynamic flows, which they were inherently looking at three-dimensional flows. And I think that there is definitely opportunity to think about ways we could apply analogous theories which follow from our results for 3D turbulent cascades. I see. So you were talking about large scale 3D with vertical motion. I was talking about small scale 3D. So there are opportunities to use these methods in small scale 3D flows. In terms of quasi-bidimensional flows, that is something that we're exploring at the moment in quasi-geostrophic systems, kind of layered systems where we can look at properties that vary with depth and how we can start to introduce potential energy as well as kinetic energy to the system and see if there are ways to measure the distinction, or see if there are ways to measure the energy cycles within those flows. Something that I didn't mention here was that this structure function is specifically measuring the turbulent cascade rates. And so there are other processes that move energy between flows, like the creation of large-scale density gradients, which can non-locally move energy to smaller scales via instabilities. And that's something that we don't measure with structure functions, but is also a really important part of the energy cycle.
All right, thanks so much, Brodie. That's we're out of time, so we'll wrap up the official talk there. Thanks.